RFID works and we see what is inside RFID tags or cards, which you use every day. More importantly, we learn why RFID tags don't need a battery or power source, which is one of the main reasons that made RFID so popular. RFID is used in many applications, like your key for the door, for checking products in libraries and shops, for supply chain management, for tollgate system, and many more. RFID stands for radio frequency identification. But what made RFID so popular? RFID could solve one of the most challenging things in electronics devices, which is power source. You see, every electronic device needs power, and if it is a portable device like your laptop or your cell phone, you need to have a battery to provide the energy for the operation of the device. And these batteries can be bulky and heavy, and you will need to recharge them or change them every now and then. But what if? What if we can send the power to the device whenever it needs it? Is it possible? Yes, it is. If we put two coils beside each other and pass the AC current through one of them, then it will induce some current in the other coil through the magnetic field coupling. And the device can use this current to charge a capacitor and work without a battery. Of course, this power will not be high enough to turn on a screen or move a motor, but it is sufficient enough for reading some data from the device. And that is what made RFID so popular, that we don't need to have a battery on the device anymore. Well, this is passive RFID, and we also have active RFIDs which do have a battery, but I think these passive RFIDs made them very popular. So an RFID system has a reader, which we can see on the left, and a tag or transponder, which we can see on the right. Now let's see what is inside this tag and how it is designed. The tags have a coil or antenna and a low power chip that can save some audio data and send them back to the reader whenever needed. In these pictures, you can see the inside of the RFID tag or card, where the antenna sits on the outside and the low power chip is on the inside. Now let's go and see how to design this chip. So which blocks do you think we need to have for this chip? Of course, we need to have the power unit which can rectify and regulate the RF signal sent to the coil. What else do we need? We need a controller unit with some memory to record the data and ID. This memory can be a simple ROM, but in many cases we need to be able to write new data to the tag, like you add some money to your canteen key, right? That's why we need to have an EPROM. What else do we need? We need the transmitter unit, of course, to send the data back to the reader, and as we discussed, we also need to write some data to the chip, so we need the receiver block as well. So these are the blocks that we need to implement for our RFID chip. Let's start by the transmitter block, because there is a very intelligent idea there that I want to share. So we mentioned that the power we send to the tag is good enough for transmitting some data. So you may think that perhaps we should have a transmitter to generate the RF signal and send it to the reader. However, the RF transmission can be quite power hungry. You need to have oscillators to generate the carrier frequency, and you need to modulate the signal to drive the antenna. This antenna is usually a very low impedance load, and if you want to have a transmitter, it will immediately empty the capacitor. So they came with this idea and said, what if we do not transmit any RF signal? Then how do you transmit the data? Here's the idea. The reader is sending the RF signal to the tag, right? We can actually put a switch across the coil in the tag, and whenever we have a binary 1 data, we close the switch, and when we have a 0, we open it. So if two coils have a coupled magnetic field, when we short one of them, it changes the inductance in the other coil, and if we have an RF signal on the first coil, it will attenuate the signal there, and the reader can use this information to see when the coil in the tag was shorted. This way we can send the information without actually sending any RF signal from tag to the reader. They call it backscatter modulation. However, the change in the signal of reader would be very low at the range of 1 to 1000 of the actual RF signal. So this change is very susceptible to noise. That's why they use some other modulation like frequency shifting or phase shifting to improve the noise rejection. In these modulations, we still change the amplitude of the source signal by switching the coil in the tag, but now, for example, for frequency shifting, we say if we give 4 cycle off and 4 cycle on, then the data is 0, and if we give 5 cycle off and 5 cycle on, then the data is 1. So this way we are coding the 0 and 1 inside the frequency. Or in case of phase shifting, we say when we change the phase of the signal, it can be interpreted as 1 or 0. Now let's move to the design of power unit. As we showed, we need to have a rectifier, and this rectifier saves the charge on the capacitor. Sometimes they also include a multiplier circuit to increase the voltage level, along with the regulator after it to regulate the voltage. So let's go to the design of controller. It can be easily designed using logic gates, but one thing I want to mention here is that we need to have an accurate clock, especially if we want to do phase shift keying or frequency shift keying for the modulation. Having accurate clock can be achieved by crystal oscillator and using PLLs. However, this is also a power-hungry block, so they came up with another idea and they said, let's use a low-power oscillator, for example a ring oscillator, and then we sync it with the incoming RF signal, because that incoming RF signal is generated by the reader and it has an accurate frequency. So again, they use the signal from reader to achieve what they want, in this case accurate clock signal. Now let's move to the last block on this tag IC, which is the receiver. The data which is sent by the reader can simply have amplitude shift keying modulation, because we can change the amplitude from the reader as much as we want and is not highly affected by the noise anymore. Then in the tag we use envelope detector to find these ups and downs in the RF signal and extract the data. So that was a rather long explanation on the design of RFID tag chips. At this point I want to discuss about RFID frequencies. RFID devices can have different frequencies. This is the information from Wikipedia showing the different frequencies of RFID, which is low frequency, high frequency, ultra high frequency, and super high frequency. But the most common frequency band is 13.56 MHz, and majority of RFID tags work in this frequency. The other thing we learn from this data is that higher frequencies provide larger distance range. For example, UHF is mainly common for the applications where a large distance is required. RFID devices are not interchangeable and the frequencies are not adjustable. That is because each frequency range requires its own antenna. You can actually figure out the RFID frequency of the device by looking at the antenna. The low frequency antenna has a thin copper wire that is coiled hundreds of turns, while the high frequency antenna will have a few turns. So the higher the frequency range, the shorter the antenna will be. Now let's talk a bit about the readers. As we discussed before, RFID readers are the units that transmit the power to the RFID tag and read or write the data to the tags, right? They are usually stationary units, therefore they can have their own power source and we have more flexibility for designing the reader. For the reader, we also have an antenna and a modulator and demodulator. There are single chip solutions available. For example, MFRC 522 from NXP is one of the examples for 13.56 MHz RFID reader. In this typical schematic, we can see that it modulates the signal and transmits it to the antenna, and the same signal goes back to the receiver input to detect the signal change due to the backscatter modulation. This one is a low-cost RFID reader board based on that chip and is using a PCB antenna. I don't go very much in detail on how to work with it because there are many videos on YouTube about connecting this board to Arduino. So in this video, what I wanted to do was to explain the main concept in RFID communication, such as backscatter modulation or power harvesting, and to explain how RFID actually works. I hope you enjoyed this video and see you later.